Hello, Math Humans. We're going to continue our work with exponential growth and decay today. And today we're going to be looking at two special cases. We're going to be looking at the doubling and the half-life. So there are two formulas. Really, we still have the same formulas, but we're going to go ahead and use these formulas because it might make the math seem easier. So the doubling time might be a situation where a bacteria doubles every 30 minutes. That's growth. And so here's our p sub 0. Remember that p sub 0 is always going to be, I'll write it over here, p sub 0 is your initial population of whatever we're talking about. And in this one, since it's doubling, our b is going to be 2, and then t is always going to be time. And then in this particular model, d is going to be equal the time to double. So however often it takes for the time to double. Okay, so it's just a slight variation of the formula that we've already used, meaning that I'm going to divide by the time that it takes the function to double. Okay. The other example that we're going to talk about today is half-life. And so maybe the example says the half-life of plutonium is 2,400 years. I lied, 24,000 years. And so the formula has changed just a little bit again. So I'll do it in a different color. So p sub 0 is always going to be the initial population. The 1/2 is going to equal our b, and so that is the half-life time. Right? That is my rate of growth or decay. And then t is always going to equal time. And then h is going to be the half-life time. Okay? So similar situations, and we'll do several examples as we walk through this. Okay? So for our first example, we're going to talk about pennies. So on April 1st, you're going to receive 1 penny. On April 2nd, you're going to receive 2 pennies, and then on April 3rd, you would receive 4 pennies. So you can notice that my pennies are doubling every day. So it says you'll receive double the amount of pennies every day until April. How many pennies are you going to have on April 30th? And since we start on April 1st, that means that April 30th means that our time is going to be equal to 29. So I would start with my p of t is going to equal, since we're talking about doubling, it's going to be p sub 0 times 2, and then it's going to be time technically divided by d, but in this case it's doubling every day, so that means that this is 1. Okay, so then if I substitute what I know, on the first day I have 1 penny. It's going to double every day, and then we said that my time was equal to 29, so if I raise that to the 29, and technically it was doubling every day, so I could divide by 1, but it's still just 29. And when you do that math, you're going to get a shocking number of pennies, 5,000,000, not a dollar sign, 368,709.12. So at the end of 29 days, you're going to have 5,368,709 pennies. That's a lot of pennies, okay? All right, so before we start our next example, I want to talk about the properties of logarithms. So there are lots of properties of logarithms. We're going to focus on one. And we're going to talk about this because we need it to solve some equations. So let's say I have an equation that says the log of x raised to the r. And notice that the r is going to move out front. And oftentimes this might be a variable, so it's a way of solving an equation. So the r moves out front, and then I could manage what's left over. So I have a quick example. So let's say I have 20 is equal to 10 times a half raised to the x. So the first thing that I'm going to do, so I want to solve for x, so I'm going to circle that because that's what I'm going to solve for, is to isolate x and get it all by itself. So that means that I'm going to divide both sides of the equation by 10. So I'm going to get 1/2 raised to the x is equal to 20 divided by 10, which is 2. Well, now I'm going to use my properties of logarithms, and so what I'm going to do is I'm actually going to take the log of both sides. So I'm going to say the log of 1/2 raised to the x is equal to the log of 2. The power rule means that that guy can go out front, and so I would have x log of 1/2 is equal to the log of 2. The goal is to solve for x, so I'm going to divide both sides of the equation by the log of 1/2, and I'm going to divide by the log of 1/2, and so I'm going to get that x is equal to the log of 2 divided by the log of 1/2. And then you can leave it like this, or you can push buttons on your calculator, and we're going to push buttons. So let me clear what's there. Okay, clear all that. So I'm going to take the log, and notice when I push the log button that it opens a parenthesis. Let me zoom in just a little bit. It opens a parenthesis, so after I put the 2, I need to make sure that I close that parenthesis and then divide it by, and then I'm going to do the log of 1 divided by 2. Now you can see that I have the same thing here as I do here, and I hit enter, and I get that the answer is a -1. So the power rule allows me to solve for x. And so we're going to use that in some of our next examples. Okay? So the next problem that we have, let me zoom back out. Example number 2 says a bacteria is going to double every 6 hours. If the initial population is 4,000, how many hours, so I'm looking to solve for time, would it take for the population to increase to 25,000? So I'm going to write down what I know first. So here's my piece of 0. We're doubling, so I know that my b is going to be 2, and it's time divided by how often it doubles. And so then I'm going to substitute in what I have. My initial population is 4,000, so I'm going to write 4,000. Here's the times 2, and then I'm going to have time, and it doubles every 6 hours, so divided by 6. And then I'm going to put this 25,000 over on the other side. So now you can see I have a nice little equation. The goal is to solve for time. So to do that, I need to divide both sides by 4,000 first. So I'm going to divide this side by 4,000 and this side by 4,000. So I'm going to get 2 to the t over 6 is equal to 25,000 divided by 4,000. 3 zeros can cancel. And I'm just going to leave the 25 divided by 4. I'm not going to push buttons on my calculator yet. So remember, the goal is to solve for t. T is in the variable position, so now I'm going to take the log of both sides. Okay? I'm not going to do this math yet because it creates a lot of error, so I'm going to wait until the end of the problem to use my calculator. By the power rule, that number, the exponent, goes out front, so t divided by 6 log of 2 is equal to the log, and again, I'm not going to do this math yet. So now I want to isolate what I'm trying to solve for, so I'm going to divide both sides of the equation by the log of 2, and so I'm going to get t divided by 6 is equal to the log of 25 over 4 divided by the log of 2. Okay, and I'm still not going to push buttons on my calculator. So the next thing that I need to do is get rid of this 6. So because it's in the denominator, I'm going to multiply both sides of the equation by 6, and then I'm going to get t is equal to, and I'm going to put the 6 up front just because it makes a little bit easier in my calculator, and then I'm going to do the log of 2. So I'm going to push buttons on my calculator. So I'm going to do 6 log, and then I'm going to do 25 divided by 4. Again, you have to make sure that you close that parentheses, and I'm going to divide by the log of 2 and hit enter, and I get that my time is equal to 15.86. And then we have to look back to the problem to know what our time units are, and it said that they were hours, and so then that would be the solution to my problem. So it's going to take 15.86 hours for the bacteria to reach 25,000. That's just disgusting. All right, so now I have a couple more examples, so let's do 3 first. So the first one says a population of flies doubles every 8 days. And again, that's yucky. If initially there are 100 flies, so that's going to be my P sub 0, how many flies after 17 days? So I'm going to write my equation, P of T is equal to P of 0. I'm doubling, so I'm going to have a 2, and then I'm going to have T divided by D as in David. So I substitute in what I know. My initial population was 100. Here's the 2. My time, in this one I know the time, so I'm going to put the 17, and I know that it doubles every 8 days. Well, now it's just a calculator exercise. I will remind you that you have to do a multiply. You can't do 100 times 2 and then raise it to a power. It doesn't work that way. So in my handy-dandy calculator, I would do 100 times 2 raised to the 17 divided by 8. And we've had this discussion before. Let me make it a little bit bigger. If you have a calculator where the exponent doesn't go up by itself and it shows you the caret when you try to raise the 2 to a power, then you need to make sure that you put that 17 divided by 8 in parentheses. Otherwise, you'll get an incorrect answer. And I notice that I get 436.20, and so I know that the question says how many flies are there, so P of 17 is equal to 436.2 of a fly is even more gross, so we're going to round to the next whole number, and I'm going to say that there are 436 flies after 17 days. All right, we have just a couple more examples. Okay, so here's example number 4. Let's scoot that up. So in this one, it's a little bit different. In example 4, I have radioactive carbon-14 is used to determine the age of artifacts. Carbon-14 has a half-life, okay, so again, critical pieces of the problem, half-life of 5,730 years. In 1947, jars containing the Dead Sea Scrolls were found, so yay archaeology. Analysis indicated that the scrolls contained 76% of their original carbon-14. Estimate the age of the scrolls. So because this is a half-life problem, I'm going to say P of T is equal to the initial population, we're talking about half-life, and time divided by the halving period. Okay, so I'm going to substitute in what I know. So, and I believe I wrote the problem down wrong. I think this is supposed to be 86%, so my bad. So as I'm looking in here, I know that my halving period is 5730, so I'm going to write this as P sub 0 times a half, and then divided by time divided by 5730, okay? So this one is a little bit unique in that we're going to go ahead and isolate this expression first. So I'm going to divide both sides of the equation by P sub 0. So I'm going to get 1/2 raised to the T divided by 5730 is equal to P sub 0 divided by P sub T. Now this is why this one is a little bit unique, and I did it upside down. Bad math, my bad. P sub T divided by P sub 0. Oops. So I know that that's equal to 86%. Okay. So now I'm going to have my equation 1/2 raised to the T over 5730 is equal to 0.86. So again, I need to solve an equation where the variable is in the exponent position. So I am going to take the log of both sides of the equation. And because I'm taking a log, that guy gets to go out front, okay? So this is going to become time divided by 5730 log of a half is equal to the log of 0.86, okay? I'm going to divide both sides of the equation by the log of 1/2, and remember we don't push buttons on our calculator until we're done, okay? Alrighty, and now I'm going to go to the back side of my paper because I kind of ran out of room. So I have t over 5730 is equal to the log of 0.86 divided by the log of a half. Now I need to manage the 5730, so I'm going to multiply both sides of the equation by 5730. And just to make it easier, when I put it in my calculator, I'm going to put this first. So I'm going to show you that math. So I'm going to do 5730 times the log of 0.86 divided by the log of 1 divided by 2. And then I'm going to close my parentheses and hit go. And I get that this is 1246.79, so 0.80. Okay, alrighty, and so I'm going to get that my scrolls are 1,246.80 years old. Now you might ask, is it okay to have a decimal of a year? Yes, absolutely, because that just means that it's some months or some days, and so we can leave it like this. All right, for our last example, we're going to talk about our plutonium. So plutonium has a half-life of 24,000 years. So underlining what's important, let's do it in a different color so you can see. Half-life, and we know that it's 24,000 years. 50 pounds of plutonium was dumped at a nuclear waste site. How long will it take for the plutonium to decay to 10 pounds? And we are looking to solve for time, okay? So let's fill in what we know. We're going to use our base formula. P of t is equal to, we're talking about half-life, so this is going to be a half, times t divided by h. So I'm going to substitute in what I know. So I know that I want 10 pounds, so I'm going to put the 10 over here. I started with 50 pounds, so it's not a population, but it's my beginning quantity. I know here's the half. And then here is my time. I'm going to try to solve for time, and I'm going to divide by 24,000 years. That's a lot of years. So to start the problem, I'm going to divide both sides of the equation by 50. And so I'm going to get 1/2 times t divided by 24,000 is equal to, those zeros cancel, to 1/5. Okay? Now I'm going to take the log of both sides because my t is in the exponent position. So I'm going to write the log, and I'm going to write the log, put parentheses. Remember, this is an exponent, so it gets to go out front. So time divided by 24,000 log of 1/2 is equal to the log of 1/5. Okay? The goal is to solve for time, so I'm going to divide both sides of the equation by the log of 1/2 divided by the log of 1/2. And so now I get time divided by 24,000 is equal to the log of 1 divided by 5 divided by the log of 1/2. Now I'm going to multiply both sides of the equation by 24,000 so that this cancels out. And that means I need to multiply by the same thing on this side. And now I'm going to push buttons on my calculator, so I'm going to do that math for you. So I'm going to clear what we have. 24,000 times the log of 1 divided by 5 divided by the log of, what did I write, 1 divided by 2? 1 divided by 2. And then I'm going to hit enter, and I get that it's going to take 55,726.27 years. Oh my goodness. So the time is going to equal 55,726 years for the plutonium to go down to 10 pounds. So there you go. That's it for today. Gotta love logs. Talk to you soon.